right, good afternoon, Ghana. Today we're going to continue with similar triangles. And I've got a problem up here I'd like us to begin working on. And I'll go ahead and mention this relates to a tactic from the hard problem from the last exam. But we're going to develop that tactic a second time here. So just to be sure, P, Q, and C are not on the same line. And I kind of wish I'd put a little bit more space between P and Q, but that's okay. It doesn't really change the problem. So let's ask ourselves the question. Let's think forward and backward. This is something you should be in a good practice of doing, is asking what would help us get to the end? What would help us prove that we have a pair of parallel lines?
The angles.
Equal angles would help us prove that. Okay. So, well, and what would give us equal angles?
Similar triangles.
Similar triangles. Occasionally congruent triangles, but you know, what do we see here that we saw in the hard problem from the last exam? I remember David asked the question, you know, how would we see this? We get another chance to practice exactly this vision. One thing that we see are two equal side lengths. What does that have to do with similarity?
We could find the side, angle, and side.
Possibly. And where would the equal lengths in this diagram fit into that, possibly? How do we go from that type of qualitative information to quantitative information?
Could we extend line PQ to touch line AC?
Possibly. I'll go ahead and say this. I don't think that does us any good in this diagram. But if you were working on your own paper, if I were a student, I bet I would have tried that. So we have three big pieces of information to work with. We have these equal angles down here where CQ bisects angle ACB. And we have a right angle. Right angles are nice in these types of problems because, well, when we have supplementary right angles, they're equal.
Can we draw a line BQ?
We can. I don't think it does us any good though. It doesn't really mesh with any of the information in the diagram. But there is something that we can do at Q.
Since would we draw, I'm not too sure about this, but would you draw a line from Q to touch B at making angle, sorry, should we draw a line from Q to touch line BC at a point maybe M to make angle CQM 90 degrees?
Another way you could say that is, let's try extending AQ until it meets.
Okay, yes,
BC.
that's a better way to say it.
Now we have two right angles at Q. What else do we have?
Two congruent angles.
Isosceles and similar triangles.
I'm going to call this point down here D. And sorry, somebody said similar triangles. Somebody said something else. What do we have that's good here?
I said we have one isosceles triangle, which is triangle ACD, and we have two, I think I see congruent triangles.
A CAQ and CDQ.
I think somebody else was about to mention those congruent triangles. Does anyone else concur?
Yeah.
Yeah, congruent triangles.
By what congruence theorem do we justify this?
They share a side and
Angle, side,
have
angle.
two angles like they share as well.
Yeah, we have ASA congruence here. Good. Okay, well, they have ASA congruence, so let's go ahead and mark anything else that we see. Those two sides must also be equal, as well as those. We have equal angles here and here. And I may have overmarked the diagram, but now let's take a step back. The information we used both the angle information, both the pieces of angle information in the diagram. We've not yet used the information about AP equaling PB. P is the midpoint of AB, in other words.
Well, when we extended AQ to line BC, we formed another pair of similar triangles.
Oh, where do you see similar triangles, Salorm?
Triangle PAQ and triangle BAD.
Good. What similarity theorem are you using?
I'm using side, yes, side.
Not side, 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 but
Side angle side, sorry.
okay, what does that do for us?
That means
It
that
tells us that
angle APQ is equal to angle ABD. So for those angles to be equal, those lines must be parallel.
Good. Nicely done. Are there any questions or thoughts about this one? So now that we've worked this problem, one thing I would say is everybody go back and take a look at the last problem on the last exam, and I think you're going to see that that problem is much more approachable. Okay, now we're going to work a very famous type of problem. We're going to call it the flagpole problem. And we're going to say we've got two flagpoles, and they are 24 feet tall and 18 feet tall. And we can assume some right angles down here. And they are 80 feet apart. Forgive me, I'm an American. I use these weird, silly units like feet. And we're going to put a wire from the top of one flagpole to the base of the other. And do it again. So now we have these flagpoles that have these crisscrossing wires, and they touch right here. We'll call that point E. We'll make the flagpoles A, B, and C, D right here. And what we're interested in is finding out how far above the ground point E is. When we draw that perpendicular down to the ground, I'll call that point F. Now, what I'm going to mention is this problem is going to have nothing to do with the fact that they meet the ground at right angles. But you can look at that later. You can see that later. This is just the setup of the problem. Now I'd like for us to identify some right triangles in this diagram. And in particular, since we want to know H, it may be good to focus on H a little bit.
Triangle EBF and triangle ECF.
E, B, F, and which one?
And ECF.
Those two triangles are not necessarily similar. In fact, I don't think they are. They share a side, and they share an angle, but they don't share anything else, so we can't get congruence or similarity.
Triangle EAB and ECD.
EAB and ECD are, in fact, similar. We're not going to wind up making use of those in this problem, but that's good. We have these parallel lines here, so that's not a terrible thing to notice.
Okay, how about if we do, if we draw a line from E and bisect it to AB, and then another line from E and bisect DC.
So before we start drawing auxiliary lines, we already have good, useful information in this diagram.
I think I found an equal angle.
Sneh?
Yeah, I think angle BAE is equal to DCE.
That's true. That's true. And that involves, somebody mentioned similar triangles ABE and CDE. But here's the thing. Those triangles don't involve EF. We're interested in finding EF.
Could you use triangle ABC and triangle EFC?
Let's make use of those. Good, non-orally. Triangle ABC is similar to triangle EFC. Therefore, AB over EF is equal to AC over EC is equal to BC over FC. Okay. Any other similar triangles that we can spot?
Yeah, triangle DBC and triangle EBF.
And I hope you're all writing out the algebra here. It's best to do this in your own hand while I'm doing it. I'm looking for what might come next. Okay, so we have some information here, and let's look up and see what it is that we know from the diagram. We know that AB equals 18 and BC equals 80. We know that DC equals 24 Here we've got BC again is 80. And then EF is right here. And EF is right here. Have I missed anything? Is there any other information that we have that I haven't marked?
DB is equal to DE plus EB.
That's true. That's true. We may save that for later. I don't know if we'll use that or not. I just mean direct information that relates to the links in the diagram. I think we have all the basic diagram information. And now let's take a look at what we have in terms of H. Well, the easiest thing that we can do is use these two right here because we have a whole lot of that information. How can we make use of these? Remember, our goal is to find H. What is H equal to?
We could cross multiply.
Cross multiply and isolate. And what is H equal to?
H equals 18 out of 80 FC.
And I'm not going to bother simplifying. I'm going to work this problem as if the goal is to work it generally, and we'll see why later. Okay? And from the other triangles, what is H equal to?
Um, 24 BF out of 80.
Okay, well, this is good. We have two different expressions for H. That's not bad. That seems like good information. And let's take a look at FC and BF. Okay. What do we know about those?
That 18 times FC and 24 times BF are both equal to 80 times H.
I'm sorry, I didn't quite understand that. What was the idea?
That 18 times FC and 24 times BF are both equal to H times 80.
Well, that's true, but on a more simple level, what's true about BF and CF?
They both add up to 80.
They add up to 80. They're along the same line segment, and it seems like we might use that.
Okay, BF and an FC sum up to 80.
Okay. You know, we isolated H in the previous equations, but what else could we do?
In the subject of BF plus FC equals 80 so that we can solve for either BF or FC.
We could try to solve for BF or FC. I think we can be more direct. Remember, we want H.
We make them variables, like if BF is X, then FC will be 80 minus X.
If it helps you out, make them into variables like X and Y or something like that. I'm going to keep them written in the classical geometric way here.
I'm not too sure, but can we just equate the two, making it 18 FC out of 80 equals 24 BF out of 80?
We could equate them to each other, but we're still gonna have to go back and find h. So here's what I'm gonna do. I'm looking at these two equations right here and I'm thinking, oh, maybe I didn't write them down in the most useful way given what we're seeing now. Maybe I can rewrite them.
May I try?
Go ahead.
So we in the BF plus FC equals AT, we could make either one of them the subject. So let's say BF equals to AT minus FC.
Oh, you're right, we could. I would rather make h the subject.
Did you find the reciprocals?
Okay. Non-Orly, I think, has the right idea here. FC is equal to 80 over 18 times h. And what does BF equal?
AT over
80
24
over
times
24
h.
times h.
Okay. Now we have two values that we can substitute for BF and FC that are both in terms of h. Oops, I've written that backward. And what do we notice about this equation?
Since the variables are the same, we can just add and then we'll be able to divide to find out our actual answer.
We can, but what's something very simple we can do to make life easier?
We can simplify it.
We can simplify it. How do we do that?
So you divide it by 8.
Divided by what?
8.
We can do better.
Mr. Crawford, isn't the second denominator supposed to be 18 and not 16?
Thank you. Let's just divide it by 80. We have 80 everywhere. And now we can factor that h out. And h equals 1 over 1/24 plus 1 over 18. And if we multiply the numerator and denominator by 24 and 18, we find that h equals 24 times 18 over 24 plus 18. And now we could go ahead and compute this if we like. What do we get after all cancellation?
72 over 7.
Okay, so now I want to point out that the 80 disappeared. The distance between the flagpoles wound up not mattering. We could bring the flagpoles together, and that point at which the wires cross still remains the same exact height above the ground. It's also true that we worked this problem without ever using 18 and 24 in any kind of computation or simplification, and we can now see that we have a general formula. If A and B are the heights of the flagpoles, then H equals AB over A plus B. Or we could say that it equals 1 over A plus 1 over B. And by the way, this number right here is half the harmonic mean. A few weeks ago, we talked about harmonic means very briefly, and this is one of the places they begin popping up in geometry. Any questions or thoughts about this one? Okay, well, this is, I'm going to title this just the flagpole problem. Okay, so at the very beginning of learning about similar triangles, I told you that we were going to take AA similarity for granted. Now we are going to work hard to demonstrate why AA similarity works. And we've seen this diagram before. I think this is the one that we used to, well, I think we've done use this diagram once before. Anyhow, so let's take a look at this. And here's the setup. Does somebody here have a little brother or sister?
Yeah, I have two little sisters.
All right, let's say that Salorm has some triangular toys and is playing with one of his little sisters. And he's showing her that because the angles are the same, these two triangles, they fit right up here. In fact, the two triangles have all same angles, let's say. So he fits the little one and the big one, and thus we have this diagram right here. And he has the sides going down smoothly, so they do fit together, except that the bottom sides don't match up because one's bigger than the other. Okay. We're going to prove here that these triangles are similar given just this information. The information that we have is two angles that are the same. Okay, what can we do here?
We can start by like giving a letter for each vertex so it's easier to refer to it.
Seems like a good idea.
And now we know that AED is the same angle as ACB.
Okay, we can mark those other angles as equal if we like. I'm going to go back to an idea, actually, an idea that we kind of skipped over discussion of, but it's a simpler concept that can maybe help us right here. And we sometimes call this same base or same height principle. If I have two triangles, let's say that we're looking at triangles P, A, B, and triangle P, B, C. And A, B, and C are all on the same line. What can we tell about these two triangles?
They share a side, PB.
That's true. They share PB. What else can we say about them? They share something else.
Total of their bases. The total of their bases form the base of triangle ABC.
That's true. We can also bring triangle ABC into the mix. And these triangles share one thing that is important. One computation.
How is ABC a triangle?
Sorry. PAC.
Oh.
Thank you. These
They
three,
all share P.
they all share P. That's true. What could we draw from P?
Altitude, maybe.
An altitude. That altitude is just the direct path, the shortest path from the point to that line. So they all have the same altitude. And look what happens with their areas because of that. The area of PAB is equal to base times height divided by 2. The area of PBC is equal to base times height divided by 2. And the area of PAC is equal to base times height divided by 2. So if we wanted the ratio of two of these areas, what is that going to equal?
(11 over 9).
Which is what?
The two
AB.
bases.
It's the ratio of their bases, and that's it. And that kind of makes sense, right? Area is this, it's this multiplication between stuff going on in two different dimensions. So if one of those dimensions is the same, it only depends on the other one of those dimensions. So this is an example of two figures that share the same height. We could also have figures that share the same base. Which triangle has the larger area, ABC or DBC?
ABC,
How do you know?
because it has a larger height.
Has a larger height. Why does the one with the larger height have the larger area?
Because they have the
Because their
same.
bases are equal. So it has to be the height that's the changing variable.
Yeah. They have the same base, and so all we need to know in order to know the ratio of their areas is the ratio of their heights. So this is a way of taking some information in length and then being able to more easily create two-dimensional computational relationships with area. So why do I bring this up? We are interested in ratios in this diagram, right? We're trying to establish AA similarity, but we can perhaps make use of other similarity. And other similarity involves side lengths. It involves ratios of side lengths. So what areas can we make use of? I'm going to draw in BE right here. And let's focus on the left side of the diagram. We have AD equals 6 and AB equals 9. So we have a 2-to-3 ratio over there. Well, it would be nice if we had like another 2-to-3 ratio, AE to EC.
And what does that make EC for?
Well, we don't know that yet.
Well, have you already considered that the triangles are similar?
We're trying to establish that they're similar using only the information that the two original angles are equal, the angles at A and B. That's our goal. We want to establish that they're similar.
Okay.
Does anybody see a place where we could use same base or same height?
Well, we can say triangle BDE and triangle ADE have a shared base, and since they share a base, they also share line DEE, which could be seen as their height. So,
Hey, Salorm, say that again for me. You said triangle ADE, and what other triangle?
And triangle BDE, they share a base.
Hold on, BDE, is that what you said? Okay, yeah. They have bases along the same line here. Okay. ADE, BDE, and also ABE, all three of those triangles have a base along that line. Just like we actually had three triangles here with bases, we had PAC also. And we could have used a ratio of PAC to PBC, which would have been 20:9. Okay. Huh. Well, there's that height. I'm going to draw that lightly in here because we're not going to focus on it from this point on. There's that line right there. Okay. Here's what I'm going to do. I'm going to say the area of A, B, E to the area of A, D, E equals 9 to 6. Okay. Well, you know, ABE contains ADE. Let's focus on triangle BDE for a moment. See that gray area? Can anyone else spot another triangle in this diagram that has that same area?
It would be BEC, right?
Did you say DEC?
No, BEC.
BEC. No, I don't think triangle BEC has the same area.
I'm going to rather be AEB.
Oh, sorry, what about AEB?
You said which other triangle has that gray area in it? Now saying AEB also has it in it.
That gray area is part of AEB. I want another triangle that has the exact same area as BDE.
I think triangle EBC.
It's not EBC. So let's talk about some parallel lines. So let's say that I've got points P1. Now let's just do A and B on one line. And then on the other line, I've got a whole bunch of points. P1, P2, P3, P4, and I'll stop at P5. And now I'm going to draw some triangles. Sorry, my work is messy. I'm going to draw these green triangles that all have side AB, and I want you to tell me which one has the biggest area.
I think all have the same area.
Manvindra is correct. All of them have the same area. Why is that?
Because they all have the same height and base.
Yeah, and height.
Good. Now go back here. Find me another triangle that has the same area as BDE.
Would it be ADE?
No. Use the parallel lines.
Triangle DEC.
Yes. I'll call it CDE. And this is really a spectacular moment. What we're doing is we've taken the area on the left side of the diagram, and we have now pushed a piece of that area to the right. And it's the same area that it was before, right? We're focusing on the numerator of these ratios. And we know that AB, that first ratio, ABE to ADE, right? We know that that is just AB to AD because they share the same height. And now we have shifted that area to the other side of the diagram. What does that allow us to do?
That means that AD over AB would be equal to AE over AC.
Okay, we're going to get there. We're not quite there. What is the area ADE plus the area CDE?
To be equal to the area of ABE.
We're focused on the shaded area in the diagram, which is this right here. What is the simplest way to say the sum of those two areas?
1 plus CDE.
I don't want us to simplify the whole fraction, just the numerator.
Since they have the same height, wouldn't that just be AC AE plus AE over AC.
Sorry, repeat.
Sorry, since they have the same height, wouldn't that be AE over EC?
Well, what is the area? We don't have anything with AC in it yet. What is the area ADE plus CDE? Those two areas are the area of what?
Triangle ACD.
Right. And now these two triangles have a same height, just as the triangles did on the other side. And that tells us that the ratio of these is AC to AE. So now what we have are ratios of two sides that are the same. We have established that AB over AD is equal to AC over AE. So let's think about what we've got for the moment. With triangles ADE and ABC, we started with two angles that are equal. We quickly said, okay, well, that means that we have three equal angles. Now we have added ratios of two sides. We just need one more piece of information. The other sides, we need to know that BC over DE is that same ratio as AB over AD and AC over AE. And let's say that we're not allowed to use any similarity theorems, because the fact is that we built our other similarity theorems off of AA. So we don't want to use any circular logic. So how do we get the other pair of sides involved?
We use the fact that the area of DEB is equal to that of DEC. So we just move the triangle from the left to the right.
Well, that's what we did to get this far. I'm asking, like, we're done with this diagram. We got we looked at the left-hand side, and this is what we did. I'm going to summarize what we did. On the left-hand side, we said, hey, look, we have a ratio of two lengths, and we're going to shift that ratio into areas in the diagram. And so we had this area and this area, and then we shifted the bottom area across the diagram so that we could shift it back into a ratio of side lengths. And that's a wonderful, spectacular way to move quantities around in a diagram, is to go between one-dimensional lengths and two-dimensional areas and back again. So now that gave us the ratio of two pairs of sides, but we need the third. So was this Salorn playing with his little sister? Is that the setup here?
Yeah.
Yeah.
Okay, so he's got these two triangular pieces. What can he do with them now? He took them and put them together at an angle, and that allowed him to examine the ratio of the sides around that angle. So what could he do with these little toy triangles now?
Mr. Crawford, could you say that again?
Yeah. You took the two triangles and you put them together to share a vertex. And by doing so, you created a diagram where we could establish equal ratios for the sides around that one angle. What can you do to get the third side involved?
We could change the orientation of our divisions of the triangle so that now we have it being like maybe it's no longer DE that is going over BC. Now it might be between BA and BC over AC. That way we can work with the other side.
Okay, you lost me a little bit. I like the idea of changing the orientation of the diagram. Here's what I'm going to say. Just dislodge the little triangle. Pick it up. Pick it up and put it back down again. How do you want to put it back down? Right, here's the big triangle. Putting the little triangle here allowed us to get information about the ratios of the side lengths. That was because we fit those angles together. How else could we place the little triangle?
You could put this to the bottom left.
Great job. We could match up those angles instead. And now we get this to this, which was AB to AD. Sorry. Oops. That to that, which was AB to AD, is the same as BC to DE. And now we have all three sides in ratio together. I apologize, I have to handle an animal. Okay, and that's it. This establishes AA similarity, and since we worked off of AA similarity to establish so much else, we are done. And this is quite an introduction to similarity in total. So now one thing that we haven't done is talked about constructions in a while. We talked about them at the very beginning when we started doing geometry, but we're going to do some constructions that we can only really understand in terms of similarity. Okay. Let's ask ourselves, if we wanted to copy an angle, right? One of the first constructions that we did was we copied a length. And that wasn't too hard. We also learned how to add and subtract two lengths and to copy that onto like a new line somewhere. Well, let's say that we have an angle and we want to copy it onto a line. What would we do?
Could we draw a circle around it?
Oops, terrible drawing. Why are we drawing a circle?
So that you can take the dimension like of the radius of the circle and use it to draw it.
Okay, I like this idea. So maybe we take this line segment here in blue and we transfer that. We already know how to transfer length. Okay, and then we draw that same circle. We hold the compass open there like that. We're almost there. How do we identify exactly where the other point goes somewhere in that neighborhood?
I'm not sure, but what if we stand on the end there? Okay, yeah. On B and open to A. Then we stand on Y and mark the circle there.
I'm sorry, say again?
Could we trace the length of AB and put it at Y to meet the circle?
Okay, yes. AB is a length right there. And here's the thing. we have a situation where we have two sides and an angle in between. We already know that there is one and exactly one triangle by SAS congruence that has those properties. So now we open our compass to AB, and we can go to Y, and we can draw a new circle with that radius. And where that circle intersects the old circle is going to be our point X, where we can draw and know that triangle OAB is congruent to triangle PXY by SSS congruence. And that determines, or that tells us that all the corresponding angles are the same. So yes, we did indeed draw this correctly. Any questions or thoughts about this? So we know how to...
I'm sorry.
Go ahead, Salorm.
Could we have also said it was by SAS congruence instead of SSS?
No, we were establishing the angle. We weren't going to assume the angle. We did not know any angles between those two triangles until we were done drawing.
Oh, okay. Thank you.
So we now know how to transfer lengths, and we know how to transfer angles. So now let's say we know how important parallel lines are, and we know how important the parallel postulate is. So let's say that we have a given line, I'll call it L, and we have a point, call it, I'll call it M. We have a point M not on that line. I want to construct a line through M parallel to the original line. How would we do that?
Is there another point on the line which has the point L?
Well, we can identify a point anywhere there. I'll call it N for non-Norley.
Then we could stand at N and construct an arc, and also stand at L and
Okay.
yes.
So we can draw a line through those 2 points. So we pick any point on L, really any point. We draw a line through the 2 points that we've identified. Now here's the thing, we don't really have the green line yet, right? We're trying to establish it. What can we do?
You could draw a circle around M.
Stand on another point L and draw a
David,
circle with a
your
radius.
internet's breaking up, David, so I couldn't hear the beginning of that. But I'm gonna go ahead and rephrase the question anyway. How can we use what we just learned, or what gives us parallel lines?
Similar triangles, similar angles.
Same angles give us parallel lines. So we want to transfer that angle. And we can do that just as we did above with a couple of circles. And once we do, what do we have?
Parallel lines.
Parallel lines. We can just extend this in both directions, perhaps with a better drawing than I made. Okay. Now we're going to use similar ideas to divide a segment into n parts. But really, we're going to focus on 3. We're going to trisect a segment. And if you can do this into 3 equal parts, you can do it into any number of equal parts. So 3 equal segments. Well, that means that we have a ratio of 1 to 3. So we can think in terms of ratios, which means that we can think in terms of similar triangles. So let's say that we've got this line right here, and I'll call this A and I'll call this B. Well, we don't really have any triangles, do we?
No.
I want triangles. I'm going to draw just another line through A. And we still don't really have any triangles, do we? Well, I'll identify a point. I will call this one R. Okay, now we can make a triangle. We can connect R to B. Okay, and we want AB to be divided into 3 congruent pieces. Now that's qualitative. Qualitative is their equal. Quantitative means that we want like a 1 to 3 ratio. What can we do in this diagram to get a 1 to 3 ratio?
Should we step at A and construct an arc, and also step at B to construct an arc and rule a straight line?
Construct arcs around A and B, circles around A and B.
Yes.
Do that on your own diagram. Draw your own figure. See if you can make that work in some way. Now, here's what I'm going to say. We picked any old point R. But we can be picky as to how we pick R. If I get the compass out and I draw an arc centered around A, now I have a length AP. What can I do with that length?
You could use it
We can keep that compass width open.
Like ice cream or something.
We can keep the compass open, put the needle down at P, and draw.
Like ice cream.
And Sneh, you've got your microphone on. And we can get another point, Q, which is the same length out. And then we can do that again. Keep the compass open, put the needle down at Q, and draw another circle or just the arc that intersects this new line. And we'll call that one R. Now we have chosen R specifically so that we have equal lengths. Now, what did we just learn how to draw?
Similar triangles.
No? What did we just learn how to construct?
Sorry, I meant similar angles.
We learned how to construct a line through a point parallel to an original line. Where would you want to draw parallel lines here?
To the points P, Q, or R.
If we draw through Q parallel to RB, and we know how to construct that line, now we can construct a point through P parallel to RB. And since these lines are parallel, those angles are all the same. And of course, A is congruent to itself. So triangle APX is similar to triangle AQY is similar to triangle ARB. And so the ratio of, for instance, AX to AB is the same as AP to AR. So this is 1/3 of the whole AB. And then similarly, AY is 2/3 of AB. And then finally, YB is what remains, same 1/3 of the total overall length. And now we have a trisected segment. Any questions or thoughts about this one? Okay, I've got one more lesson using similarity. We're going to talk about the angle bisector theorem. How many of you have heard of the angle bisector theorem? Have you learned to make use of it?
Well, what I know about the angle bisector is that you can use it to inscribe a circle inside of a triangle.
So that's true. That's true. I wish we had more time to discuss that avenue of exploration, because that's when we get to centers of triangles, that's a whole lot of fun. By the way, let's have a quick question. Suppose we were to have some sessions after the summer. We could do some things like that. How many of you here might be interested in doing some continued problem solving sessions?
Yeah, I'd be pretty interested in that.
Yeah, that'd be fun.
Okay, so at least a few people would be. I will talk to Joel about that possibility. We'll see what we can do. Okay, let's talk about the angle bisector theorem. We're going to start with any old triangle. Any old triangle. We're going to assume nothing at all special about it. But we want to generate information. And one of the ways that we've learned that we can sometimes generate information in an interesting way is to use the parallel postulate. We don't have any parallel lines in this diagram though. So I'm going to draw one. Now previously, in order to prove like there were 180 degrees in a triangle, we drew a line through A parallel to BC. I'm going to try a different exploration this time. I'm going to draw a line through C parallel to AB. And specifically, I'm going to do this in a diagram where we have split the angle at A into two congruent pieces. So we have an angle bisector. And we go, okay, well, what else is going on in this diagram? I'm going to call this point D that is on BC, and where the parallel line meets the angle bisector, I'm going to call that E. Of course, we could continue drawing that angle bisector out to infinity, but that's all we need. So, interesting stuff going on in this diagram. What do we have?
Managed to form new triangles.
We've formed some new triangles. Okay. What about the simple stuff? We have parallel lines. So do we have any like new angle information?
Yeah, we have BAD is equal to DCE. AD.
Wait, hold on, slow down. BAD is equal to what?
DCE.
BCE, is that what you said?
No, DCE.
DCE?
Yeah.
It's not DCE that's equal to BAD.
Sorry, BAD is equal to DAC.
Well, we already know that BAD is equal to DAC. But because of the parallel lines, focus on the parallel lines and focus on transversal AE.
Oh, sorry, I see my mistake. I read DE, not DEC.
Okay, this angle right here. Yeah, we have those alternate interior angles right there. Okay. There's something that just happened. The moment we marked that angle at E, a special triangle appeared in the diagram. Does anybody see it?
Yes.
What do you see?
DEC.
No, not DEC.
GEB.
Oh, AEC.
AEC is an isosceles triangle. Therefore, AC is equal to CE. Yeah, equal angles tell us those sides are equal also. Great, fantastic. Well, we also know, for instance, that this angle here is equal to this angle here. So where are our similar triangles?
A triangle DAB is similar to triangle DEC.
And I think I said things in a different order than you, but that's okay. So, okay, good. We have similar triangles. Let's write out the ratios. AB is to EC as AD is to ED as BD is to CD. So I'm looking at these and I like some of these links. Some of these, okay. Some of these have nothing to do with our original triangle. And what I would like to do is to be able to make some statement about the original triangle itself with nothing else added. So what can we replace in these ratios? BD is part of the original triangle, CD is part of the original triangle, AD and AB are both part of the original triangle, but EC and ED, like these aren't parts of the original triangle. I'd like to get rid of them if possible. Which one can I get rid of?
Then we could make EC AC instead.
Yes, EC
And
is really just AC. And now what we've got are these two ratios. And if we want, we can rearrange them. We can say that AB over BD equals AC over CD. And this right here is one version, and this can be written in multiple ways, but I'm going to call this the angle bisector theorem. And in fact, I'm going to give it an intuitive description. Does anybody know what a teepee is?
I've seen them before. Aren't they those small huts that have 3 poles that cross together and like an animal skin wrapped around it or something?
Yeah, in some parts of the world, people would make portable homes very often. And it might be 3 poles, it might be some other number, depends on how big they would make them, but it would be kind of cone-like or pyramid-like or something like that. And we might have those sticks maybe sticking out the top. Maybe just a little light could get in. I like to tell this story as the triangle is like a teepee and the light goes overhead. And throughout the day, there is one position of the sun up here somewhere, such that when the light goes in, it creates precisely equal angles on both sides. And when it does, the ratio of the shadows is the same as the ratio of the sides. AD is to AB as DC is to AC. And that's just a rearrangement of what we wrote right here. Or you could say the length of a side to its shadow is constant between the two sides. So anyway, that sort of intuitive description always made it a little bit easier for me to think about exactly what that is that's going on. So let's work a few problems that involve the angle bisector theorem. I apologize, in the book that I'm using, I've got to move to a different part of the book. The angle bisector theorem is one of those theorems you will use a lot now because, really up to this point, we haven't developed a lot of computational tools, right? We've mostly focused on qualitative observations and a little bit of ratios here and there, relationships between angles. But let's make sure that we get some practice here. What's the length of side AC?
$14.
14. Yeah. The length of a side to its shadow, the length of the other side to its shadow. 12 over 6 is AC over 7, and AC is 14. Okay, good. More common situation as far as making use of the angle bisector theorem is that we know all three sides of a triangle, like 8, 9, and 12, and then we bisect an angle. And we want to know the sizes of the pieces into which it bisects, or into which it cuts side AC. Somebody tell me, what are the lengths of those pieces AE and EC?
A is equal to 12 minus EC.
True. They have a relationship where they sum to 12. What does the angle bisector theorem tell us directly?
BE is the angle bisector.
BE is the angle bisector, therefore
BC over EC is equal to BA over EA.
good. And we know some of those lengths. BC is 8, and BA is 9. And we know that EC plus EA is 12. Solve for those.
That means that EE is 12 times 9 out of 17.
True. That's AE, and what's EC?
96 out of 17.
Good. And I'll go ahead and tell you how I actually do this. So we could, we're just solving this system of equations right here. Not that bad. But I'll go ahead and tell you, I like to use one variable, a parameter, where possible. I might say, hey, look, AE is going to be 9x, and EC is going to be 8x. And then I know that 9x plus 8x equals 12. So x equals 12 17ths. And so 9x equals 9 times 12 17ths, and 8x equals 8 times 12 17ths. Okay, good. That's an example of, there are a couple of examples of uses of the angle bisector theorem. Very, very common. You'll find yourself doing this a whole lot. Okay, the next thing we're going to do is we're going to get into right triangles. And I will post a document on right triangles after this class. Excuse me, I'm actually going to go refill my water, and then we'll come back and we'll get started with right triangles. Okay, well, we've already talked some about right triangles, and I'm sure you all know plenty about right triangles. And we even proved the Pythagorean theorem the other day, and I'm going to point this out. I came across a website a number of years ago. I haven't been there in a few years, but I've been 2 or 3 times. It had over 100 different proofs of the Pythagorean theorem. That's how connected the Pythagorean theorem is to so much math, is that you can get there from all kinds of different ways. And given that we only have about 30 minutes left in class, I'm just gonna approach some playful explorations. We're not gonna do the heavy geometry side. We're actually gonna talk about what we can do with Pythagorean triples. Does everybody here know what a Pythagorean triple is?
Yeah, we looked at them in the previous class, and they were when you squared the two sides and two of the sides and you sum them to find the hypotenuse would be a perfect square.
Okay, we're going to deal only with the integers. You know, the fact of the matter is it's very rare, ultimately, for a right triangle to have integer side lengths or even side lengths in integer ratios. But one very simple one that probably all seen is a 3, 4, 5 right triangle. So let's make a quick list. What, you know, off the tops of your heads, what Pythagorean triples do you know?
3, 4, 5. 6, 8, 10.
Okay. And here's the thing. These sides are in ratio 3, 4, 5 also. I'm going to call the first one a primitive Pythagorean triple. And the second one is merely a Pythagorean triple. Now, the fact of the matter is, if you know the primitive Pythagorean triple, all you have to do is multiply it by all the side lengths by some scalar, by some factor, to get the new one. Because if 3 squared plus 4 squared equals 5 squared, then multiplying all of that by 2 squared and now we've got 6 squared plus 8 squared equals 10 squared. And it didn't have to be 2. I could have let 2 be any integer n. And we would have found that 3n, 4n, 3n, 4n, 5n is a Pythagorean triple. So for the most part, we're just going to focus on the primitive Pythagorean triples, the ones that have side lengths that are relatively prime with one another. If we can do that, we can find all the rest. So what is another primitive Pythagorean triple? We've got 3, 4, 5.
9, 12, 15.
That one's not primitive. That's another 3, 4, 5 right triangle. Nine, 12, and 15, they all share the common factor 3. I want one where the side lengths do not share any common factors.
5, 12, and 13.
5, 12, and 13 is one. Okay. Anybody else know any more?
7, 22, and 23.
I heard 7. What were the other two sides?
Oh, sorry, I made a mistake. I meant 24 and 25.
7, 24, and 25. Okay. So I'm going to make a quick list and see what we can do with that list. See what we learn from it. One thing that I noticed is that for each of these triangles, each of them has a leg that is a small odd number. 3, 5, 7. What else do we see?
There's another one which doesn't have a small odd number.
What's that?
8, 15, 17.
That's true. 8, 15, 17 is a primitive Pythagorean triple, and none of the sides are particularly big. That's true. We're going to focus, we're going to leave 8, 15, 17 on the sideline for now. We're going to focus on these 3 because they all have some interesting similar characteristics. 3, 5, 7. What else do we see among the other numbers?
The first numbers are odd, so they are increasing by.
C is always 1.
Okay. Okay, the difference between B and C is always 1 for all of these. So, all right, C minus B equals 1. What else?
So far, A seems to be increasing by 2 every time.
We seem to be using just odd numbers here. Okay.
C is increasing by 8. No, sorry.
B increases in multiples of 4.
B increases in multiples of 4. That's true. 4, 8, 12.
B
And so far, C also
C equals
increases.
A squared.
Ah, somebody just said it. C plus B equals what?
A
A
squared.
squared.
Good. Yeah, B plus C equals 9, 25, and 49. And this is no accident at all. If we started with the equation A squared plus B squared equals C squared. Now, there's not much algebra that we can apply just flat out to this equation. On the other hand, if we were to move B squared to the right-hand side and rewrite this as A squared equals C squared minus B squared, now we can factor a difference of squares. A squared equals C plus B times C minus B. Now that's interesting. If we pick C minus B equals 1, then we just have A squared equals C plus B. Not only that, if B and C differ by 1, then one of them is even and one of them is odd, right?
Yes.
Yeah.
One of them is even and one of them is odd. So A has to be odd.
Wow.
A squared is B plus C. B plus C is odd. So A squared has to be odd. So let's try another one of these. What if we started with 9?
40 and 41.
Right. We square 9, and then we just divide it in 2, rounding up and rounding down so that they differ by 1. Similarly, 11 and
60 and 61.
yeah. There's no reason we can't do this for any odd number. So let's figure out what it looks like in general. Let's say that our odd number is 2n plus 1. What do we do with this number?
We multiply it by 2. No, we squared, my bad.
When we square it, we get 4n squared plus 4n plus 1. What do we do with this to get the 2 other side lengths?
We divide it by 2.
We divide it into two roughly equal pieces, round up and round down. What are those roughly equal pieces?
B and C.
What are they in terms of n?
2n squared plus 2n plus 1. And the other one will be 2n squared plus 2n.
Good. So 2n plus 1, 2n squared plus 2n, and 2n squared plus 2n plus 1 will always form a primitive Pythagorean triple. And that's kind of cool. We now know that every odd integer greater than 1 is the leg of at least one Pythagorean triple. Well, that's kind of nice. Is there any integer greater than 2 that cannot be the side length of a Pythagorean triple?
I don't think so.
I'm going to leave this as an open question for the moment. I'm going to leave this for all of you to explore. Can you necessarily construct a Pythagorean triple with every side length greater than 2? So now look at 8, 15, 17. This didn't fit the same pattern. However, it's still true that a squared plus b squared is c squared. So a squared equals c squared minus b squared, which is c plus b times c minus b. Let's see how this works out in the 8, 15, 17 case. Well, if we let a equal 8, then we've got 17 plus 15 times 17 minus 15, which is 32 times 2. And that's 64, and that's 8 squared. So here's a challenge. I want somebody else to find another primitive Pythagorean triple where c minus b equals 2.
Twelve, 35, and 37.
Okay, 35 and 37, where 37 minus 35 is 2. And then 37 plus 35 is 72, which is 2 times 6 squared. And then we have 12 squared is equal to all of that. So yes, 12, 35, 37 is in fact a Pythagorean triple. Nice work. Anybody else want to come up with one? $32 was 2 times 4 squared. 17 plus 15 was 2 times 4 squared. 37 plus 35 was 2 times 6 squared. What else could we do?
I'm seeing a growth of 4 with a, like each one of them is a multiple of 4. So I'm guessing the next one could be 16.
And we want the difference between the hypotenuse and the larger leg to be 2. So what do we want the sum to be?
2, 8 squared.
Yes. So what are those side lengths going to be?
I think 99 and 101.
Now what's 2 times 8 squared?
188.
128.
128.
So it will be 130.
What are our side lengths?
62 and 66.
Oh, that's close. They need to differ by 2 and add up to 128.
63 and 65.
That's right. 16, 63, and 65 are a Pythagorean triple. And in general, 4n, and then I think 4n squared minus 1 and 4n squared plus 1. All of these Pythagorean triples fit that form.
So, Mr. Crawford, how does that work? Since we just discovered that C minus B is equivalent to 1.
No, C minus B was equal to 1 in these examples up here. But it doesn't mean that C minus B always has to equal to 1. We were just exploring some where that was true. For these, C minus B was equal to 2. And here's the thing. We're multiplying the sum and the difference between the hypotenuse and the second, and the largest of the two legs, right? And we have this, we need this for this to be a perfect square when we multiply it all together. And we have a 2 over here, right? So we need the other thing to be 2 times a perfect square so that we can pair up that extra 2 and still have a square. So could C minus B be something else?
So it's not a general rule that, oh, every single time C minus B is 1.
It's not a general rule. We've already seen that C minus B can be 2. And in fact, we can always rearrange the side lengths, right? Right? There's no reason why we label the smaller leg A. You know, we could have said, hey, look, C minus B is 18, or C minus B is 32. So no, there's no general rule like that. However, if we say, hey, A squared is C plus B to C minus B, one nice way to discover is to say, hey, we can make something work if both C plus B is a perfect square and C minus B is a perfect square. Right? If both those things are true, then certainly A equals M times N. So can you pick two numbers whose sum is a perfect square and whose difference is a perfect square? I'm going to leave that as a challenge for a moment. Spend a couple of minutes, see if you can come up with one.
Does 1 count as a perfect square?
1 is
Yes.
1 squared.
Okay.
So pick another one though, because we've already explored the ones where C minus B is 1 squared.
Okay.
Ooh, we could have 4 squared and 2 squared. as our C and B. Coming.
I think that would give us the 6, 8, 10 triangle.
Um,
And that's fine. Let's take a look at that. If we let M equal 4, and N equal 2, now here's the thing. B and C have the same parity because their sum and difference have the same parity. C is going to be 4 squared plus 2 squared over 2, which winds up being 10. And then B is 4 squared minus 2 squared over 2, which winds up being 6. And A winds up being 4 times 2, which is 8. Let's pick some bigger, more spectacular values for M and N. Let's just see what happens when we let M equal 17 and N equal 11. I don't know what this is going to result in. I want to pick some crazy numbers here and say, okay, C plus B equals 17 squared, which is 289. And then C minus B equals 121. What are C and B?
There are a lot of, it could be.
There's only one possible value that, ordered pair that satisfies this equation.
well, it's going to end in, because that's the only way it can end with 9. It can be 13 because 13 is 169. Greater than 20.
Hold on, I'm just constructing that perfect square and that perfect square, but I want to know what B and C are.
I think 205 and 84.
205 and 84, okay?
Yeah,
84,
that works.
So we have A squared plus 84 squared equals 205 squared, okay? A squared equals 205 squared minus 84 squared, which is 205 plus 84 times 205 minus 84, which is 289 times 121. And A is just 17 times 11. So A, B, C is 187, 84, and 205. And those three numbers do not share any common factors. So 84, 187, 205 is a primitive Pythagorean triple. And I bet it's not one that you've ever heard of.
No.
I don't even know if I've come across this one in my lifetime. No idea. It's possible. Maybe it popped out of some problem that I worked years ago, but I don't think I've ever seen this one. And you can just invent them at will. Let's do another one. I picked 17 and 11. Somebody else pick a couple of numbers that we can square and see what happens.
No, sorry. 5. No, I'm repeating myself.
Okay, 5 and something else.
13.
5 and 13. Okay, let's see what happens. If we let C plus B equal 13 squared and C minus B equal 5 squared, so that A equals 13 times 5, and we need to solve for B and C.
Hello?
Yes? I'm waiting on
I
somebody
thought it
else.
froze.
What are B and C?
97 and 25. Oh, sorry, yeah. Wait, I think it's 97. No, 97 and 72.
There we are. That is a primitive Pythagorean triple. Yeah, this one is interesting because the numbers are kind of close together. Usually, both B and C are kind of out, one of them is outpaced, or one of the legs is outpaced by the hypotenuse. These are kind of close together, as it turns out. But I just want to check just to be sure. 65 squared is 4225. 72 squared is 5184. We add those together. We get 9409, and that is 97 squared. By the way, what's an easy way to square 97?
Square 7, square 19, add.
We
Maybe
could
100 minus
multiply.
3 times squared, yes.
And that's something you can do in your head. In fact, 99 squared is 10,000 minus 200 plus 1. 98 squared is 10,000 minus 400 plus 4 plus 2 squared. What is 96 squared?
10,000 minus 800 plus 4, 816, which is
Okay. Let's do one more. Let's see. There are occasionally Pythagorean triples. Well, actually, I don't know if we have enough math. This may be too much number theory, but I'm going to throw this out as an exploration. 3, 4, 5 is not the only Pythagorean triple with consecutive legs. Right here, we explored where a leg and a hypotenuse were consecutive integers. But every now and then you can have consecutive legs. So it might be A plus 1, and C. That might be an interesting exploration. Then we might even ask, no, I'll just leave it at that. I'll say consecutive legs, and we will pick up on Wednesday with right triangles, and we're going to spend more time with the actual geometry of right triangles when we do. Any questions or thoughts before we go? See if you can come up with any more spectacular primitive Pythagorean triples. And I'm going to go ahead and say this. The studying that we've done with similar triangles it is absolutely the most important problem-solving skill to develop in geometry, is to understand how the similar triangles fit into so many different problem-solving avenues. So, spend the most amount of time on that material, and I will see you all on Wednesday.
Thanks, Mr. Crawford.
Have a good day.
See you on Wednesday.
You're welcome.
you.
Thank you, Mr. Crawford.
Okay, thank you. Bye.
You're welcome.